Hello everyone, my name is Zheng, and I will be representing my team to present our standard abstract titled Digital Rock Imaging using GAN. Let us begin with a brief summary of my presentation. First, I'll be describing the problem statement. Next, I will present a brief introduction towards neural networks. In particular, I will focus on the two main models in our abstract, autoencoders and GANs. Due to time constraints, I will only be providing a simple, intuitive understanding of the two. Interested members of the audience are free to discuss with me or read up more on the topics in their own leisure. After the introduction, I will briefly summarize the current approach to digital rock imaging problems which uses neural networks. In particular, as we are working with autoencoders and GANs, my focus on current approaches will only cover autoencoder models. In general, there are also other types of neural networks, like LSTMs, that have seen popularity in handling 3D data, though their applications are mostly in other fields like 3D modeling. Again, interested members of the audience are free to discuss with me or read up more on the topics in their own leisure. Next, I would like to introduce our proposed method for solving the problem. We will present an outline to our approach and deliver some motivations to better motivate our choices. Finally, we present some preliminary results to test the feasibility of the method. As an extended abstract, our main focus is to show how our method is feasible to produce good preliminary results. We will not be comparing our method with other state-of-the-art methods, as these are preliminary and more fine-tuning needs to be done to ensure results can compete with their methods. With that out of the way, let us begin proper. I will first describe the problem statement in words. Given an incomplete scan for a 3D micro-CT image, our goal is to reconstruct the original 3D micro-CT image. In addition, we work on an assumption for the digital rock images. We require that the rock is isotropic. Some examples include Metamer sandstones. The reason for this property will be motivated later. Pictorially, we can understand our problem as follows. Let us represent an original 3D micro-CT scan as a cube-like structure, and our scans as 2D slices along the z-axis. So, each 3D segment is composed of multiple slices along a single axis, something like the images to the right. Micro-CT plays an important role in digital rock physics, but has limitations in, for example, being expensive or time-consuming. What we can do, however, is to consider another approach to the problem. Suppose that we only have limited slides along a certain layer, something like the cube to the right. What we want to do now is to reconstruct or inpaint along the missing slices and recover our original 3D micro-CT image to the left. This leads to our problem statement again. That is, we aim to recover a 3D micro-CT image from an incomplete scan. For those that have some understanding of image processing and neural networks, you may have realized that this problem is very much like the regular inpainting or recovery methods in 2D images, with an added touch that we now work on a 3D problem. Thus, a common approach towards related problems are in three-dimensional neural networks, specifically generative networks like GANs and autoencoders. Let us now begin with an introduction to autoencoders. One could understand autoencoders as a function that maps input images to itself. Basically, the function behaves like an identity map with a twist. The twist is that we model this function with two other functions. The first is a contractive map called the encoder, which maps the image to a smaller feature representation of the image. The second is a decoder that reverses this process. Together, the two functions are trained to minimize a distance function d as seen below. Some examples of d would be L2 norm or other related LP norms. In layman terms, we are finding the parameters for the encoder and decoder that are best able to compress and reconstruct images such that the final reconstruction is very close to the original image. Of course, in the event of noisy input data, like in painting, input image will be both noisy and clean training data, while the output of the autoencoder is the filtered, clean original image. Thus, the encoding process in this case also serves as a filtering component in the application. Such a model is popular to solve digital raw image problems. In this slide, I present some present approaches using autoencoders, of course with some adjustments to structure, which are proposed to directly process 3D images. The images on the right shows how these models are being implemented. However, such approaches come with their own set of problems. In particular, the size of 3D neural networks are much larger than their 2D counterparts. Also, training data now requires 3D samples and are generally harder to acquire in large numbers. Finally, the smoothness of autoencoders also presents more problems to reconstructing fine details. That is because the distance function during optimization tends towards a weighted average of the samples that encode to the same feature vector, which promotes smoothness. There is the need to improve the generation results using other methods. And this is where GAN comes into play. Instead of matching input image to output image, GANs approach image generation through a two-player zero-sum game. In this game, the generator G aims to generate images from a predefined noise distribution, like Gaussian normal. On the other hand, a discriminator D aims to learn to differentiate between real and synthetic images. Thus, during training, G is trained to generate images that fool discriminators, while D is trained to differentiate between real and fake images. Such training methods are based on the importance of details. As such, it is well understood that should the training converge, GANs tend to produce high detailed representations of the image. Of course, comparatively, since G does not observe the real image directly, it is usually difficult to design a GAN to carry out reconstruction tasks. Thus, we propose a unification method to combine the advantages in GAN and AEs, while ensuring that their training does not interfere with each other. That is, we do not want to merge the GAN and autoencoder into a single model for training, like in present applications. The approach we propose is based on the invert GAN problem. Lipton and Tripathi describe a direct optimization method to solve an invert GAN problem, which they summarize by the below equation. In this equation, the objective is to search for the noise vector which, under a fixed generator G, is able to produce a generated image similar to the original image X. The image is then recovered by the approximation GZ star. Others have explored this application by considering alternative options for D. For us, we propose to use a similar objective to unify GAN and AE. The below is an overview of our plan. First, on the left, we have the incomplete 3D CT scan with images along the XY axis. Due to the isotropic nature, we can also consider images from an alternative direction, say the YZ axis. Here, we then observe that each slice along the x-axis is then a 2D image with an unknown region, which is labeled yellow in our images. We then want to train a 2D autoencoder and GAN to solve the in-painting problem. Following this, we can then concatenate the 2D samples along the x-axis to recover the original image. What we have done is that we describe how we can convert such a 3D problem to multiple simpler 2D objectives and solve the problem from a 2D method through AE and GANS. This is motivated from the below points. First, the isotropic properties allows us to consider 2D objectives along any perspective. From a 3D CT scan, we can then produce much more 2D training data compared to 3D data by considering all these other perspectives. This leads to our second and third motivation, the advantage of 2D to 3D in terms of the data and the model. It is much easier to obtain 2D samples rather than 3-dimensional data, and the resulting training model can then be more accurate and smaller due to us working with 2D samples only. Rather than a direct autoencoder problem like current work, the need for fine details motivates our use of GANs, which perform better detail-wise than autoencoders. However, we want to separate the training objectives for GAN and autoencoder, as, for example, the L2 type of loss in autoencoders promotes smooth images, and we also wish to maintain the property that the GAN does not observe any training data directly, and is solely focused on detail generation to fool the discriminator, rather than trying to copy or trying to remember what the training data is. Pictorially, the training process is better summarized in the below diagram. First, we pre-train again using training data. With the samples generated by the GAN, together with the training data, we can then use it to augment the autoencoder training data to train the in-painting objective. That is, we train with both randomly in-painted patches and the original clean images, and during training, we minimize the distance between the both of them. Next, we take the generator G and the encoder E and assemble our generative encoder structure, which we call GE, like in the below image. Finally, we solve the problem using an optimization method, like in invert GAN, given by the below function. Let us look at each part first. I here denotes the in-painting mask, which is known. Of course, EG represents the encoder and generator respectively, and M is the encoded representation of the in-painted 2D image, so it will be E EIX. Thus, in the first term, EIGZ can be seen as the encoded representation of an imprinted generated sample, while M is the encoded representation of a target imprinted sample where X is unknown. Together, the first term tries to search for a Z in the noise distribution space that generates a sample which encodes into the same feature vector as the target sample. The second term regularizes Z to be closer to 0, which is in line with the fact that most GAN uses normal distribution as noise. With this, we present some samples of preliminary results generated using the GE method. In this part, we build our model using progressive GAN as the generator and a convolutional autoencoder as our autoencoder. We train the model on a training dataset of 2D micro-CT image slices along multiple perspectives obtained from the Digital Rocks portal and test the results on the testing set. In here, the red patch highlights the imprinted regions. We see from the left that the generated samples are very accurate to the original data, while close-up inspection reveals that while the images are lacking in some minor details, we are able to reconstruct most of the details with much clarity. This shows the feasibility of our proposed method to solve the problem and serves as a good baseline for us to further improve the results subsequently through methods like fine-tuning the model to try to improve the detail generation results. So before we end off, we would like to list down the references for images and other works referenced in our presentation. For interested readers may refer to them for further reading. With this, we end our presentation. Thank you for your attention.